Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
1954 Linus Pauling structure of proteins to hydrogen-bonded helical configurations of the polypeptide chain. The edifice of modern structural biology rests upon a foundation of a few seminal papers, documents whose intellectual force reconfigured the scientific landscape. Among these, the 1951 publication, Linus Pauling and Robert Corey, often retrospectively viewed through the celebratory lens of Pauling's 1954 Nobel Prize, stands as a paragon of theoretical deduction. This essay undertakes a profound and granular evaluation of the internal claims, logical architecture, and methodological rigor presented within that specific work, the structure of proteins' two hydrogen-bonded helical configurations of the polypeptide chain. We will proceed by dissecting the paper's arguments in their original sequence, assessing the validity and ingenuity of each claim as it is presented. The purpose is to move beyond mere historical appreciation and engage directly with the intellectual machinery of the paper itself, exploring how from a set of simple, powerful chemical axioms, a vision of biological complexity emerged with startling clarity and precision. This analysis will treat the document as a self-contained logical proof, examining its premises, its deductive steps, and the enduring power of its conclusions. Section 1. The axiomatic foundation of the planar peptide bond. The paper commences its argument by establishing its central, non-negotiable constraint, the precise geometry of the polypeptide chain's fundamental repeating unit. The author's primary claim in this opening section is that the peptide group comprising the carbonyl-carbon, the carbonyl-oxygen, the amide nitrogen, and the amide hydrogen is a rigid, planar entity. This claim is presented as a direct consequence of resonance theory, a cornerstone of Pauling's own contributions to understanding the chemical bond. The argument posits that the carbon-nitrogen bond within the peptide's linkage possesses approximately 40% double bond character. This partial double bond character severely restricts rotation around the bond, compelling the 6 atoms involved, including the 2 adjacent alpha carbons, to lie within a common plane. The evidence marshalled for this foundational claim is derived from the meticulous X-ray crystallographic analysis of simple, related molecules such as diketopiperazine and various amides. By using these small molecules as proxies, Pauling and Corey built their entire theoretical edifice upon a piece of experimentally verified, quantitative stereochemistry. They specify the bond lengths and angles with an air of finality. The carbon-nitrogen distance is 1.32 angstroms, shorter than a typical single bond, and the angles around the carbon and nitrogen atoms are all close to 120 degrees, consistent with sp2 hybridization and a planar arrangement. This section's power lies in its strategic reductionism. It reframes the infinite combinatorial problem of protein folding into a more tractable exercise of assembling a chain of rigid, interconnected plates. The claim is absolute and forms the first filter through which all subsequent structural possibilities must pass. Section 2. The energetic and geometric imperatives of the hydrogen bond. Building upon the rigid framework of the peptide backbone, the authors introduce a second major postulate concerning the formation of hydrogen bonds. The central assertion of the section is that for a polypeptide configuration to achieve maximum stability, every available proton on an amide nitrogen must form a hydrogen bond with a suitable acceptor, which is invariably a carbonyl oxygen atom from another peptide group. This is presented as an energetic imperative. The authors claim that the energy of this NHO hydrogen bond is substantial enough that any structure leaving these groups unsatisfied would be thermodynamically unfavorable. Beyond this energetic claim, they make a crucial geometric one. The optimal hydrogen bond is essentially linear, meaning the donor nitrogen, the hydrogen, and the acceptor oxygen atom should lie on a straight line. Furthermore, they specify a characteristic length for this interaction, with the nitrogen to oxygen distance being approximately 2.79 angstroms. This set of claims further constrains the folding problem. The polypeptide chain must now arrange itself in space to satisfy both the planarity of its constituent peptide units and the geometric and energetic demands of comprehensive hydrogen bonding. The sourcing of this information, again, comes from crystallographic studies of small organic molecules where hydrogen bonds were observed and measured with high precision. This section thus establishes the primary cohesive force that will organize the rigid peptide plates into a coherent, three-dimensional structure. It transforms the problem from one of pure geometry to one of energy minimization, dictated by the satisfying of these specific intermolecular interactions. Section 3. The deductive leap to helical symmetry. Having established their two fundamental axioms of stereochemistry and energetics, Orling and Corey proceed to the core of their deductive argument. The principal claim of this section is that the most rational and stable way to arrange a chain of identical units, each subject to the same set of constraints, is in a helical configuration. A helix possesses the unique property that every residue in the chain, excluding those at the very ends, occupies a structurally equivalent position relative to its neighbours. Each residue undergoes the same translation along the helical axis and the same rotation around it to become the next residue. This claim of equivalence is a powerful simplifying assumption. It suggests that the stable core of a protein will be a regular repeating structure. The authors frame the search for protein structure as a mathematical problem finding the helical parameters, specifically the unit rise and the unit twist, that allow a chain of planar peptide groups to form a continuous, linear array of hydrogen bonds parallel to the helix axis. This section represents a critical intellectual pivot. It moves away from the direct interpretation of the diffuse and confusing X-ray diffraction patterns of proteins themselves, patterns which had confounded investigators for decades. Instead, it proposes that the structure can be solved theoretically by finding what arrangements are chemically and sterically permissible. The elegance of the argument is its foundation in pure reason, a search for an ideal form dictated by the laws of chemistry, which could then be checked against the messy reality of experimental Section 4. The alpha helix, a structure of unprecedented specificity here. The paper unveils its most celebrated and enduring proposal, the alpha helix. The claim is breathtaking in its specificity. Pauling and Corey describe a right-handed helix defined by a hydrogen bonding pattern where the carbonyl oxygen of an amino acid residue, designated as residue N, forms a hydrogen bond with the amide hydrogen of the residue at position N+4. This precise connectivity results in a 13-atom ring closed by the hydrogen bond. They present a structure with 3.6 residues per helical turn and a pitch, or the distance the helix rises per turn, of 5.4 angstroms. The proposal of a non-integer number of residues per turn was a particularly audacious and brilliant claim. Previous models had almost exclusively considered helices with integer-fold symmetry, as these seemed more intuitive and were consistent with the symmetries observed in simple crystals. The 3.6 value, however, was a direct and unprejudiced outcome of their calculations, which sought to optimize the hydrogen bond geometry and relieve any steric hindrance between adjacent atoms. They claim that in this alpha helical conformation, all bond angles and lengths remain within their ideal, low energy ranges, and the peptide planes are oriented in a way that allows for the formation of strong, linear hydrogen bonds that run nearly parallel to the central axis of the helix. The core of the structure is claimed to be efficiently packed, with the van der Waals surfaces of the atoms in snug contact. This section presents the alpha helix not as one possibility among many, but as a uniquely satisfactory solution to the stereochemical puzzle they had constructed. Section 5. The gamma helix, a theoretically plausible yet flawed alternative in a testament to the thoroughness of their deductive method. The authors present a second helical structure, which they name the gamma helix. The central claim of this section is that another hydrogen bonding pattern is also theoretically possible. This structure involves a hydrogen bond between the carbonyl oxygen of residue N and the amide hydrogen of residue N+5. The resulting helix is wider and more loosely packed than the alpha helix, The authors specify its parameters as 5.1 residues per turn and a pitch of 5.3 angstroms. The crucial part of their evaluation, however, is their own internal critique of this proposed structure. They claim that the gamma helix is almost certainly less stable than the alpha helix. The reasoning provided is twofold. First, the bond angles within the polypeptide backbone are slightly strained from their ideal values to accommodate this wider helical form. Second, and more significantly, the hole running down the center of the gamma helix is too narrow for a water molecule to fit but too wide for efficient van der Waals packing. This creates an energetically unfavorable void. The presentation of the gamma helix is a masterstroke of scientific rhetoric. By proposing a plausible alternative and then demonstrating its energetic inferiority based on their own criteria, they strengthen the case for the alpha helix. It shows their search was exhaustive and their choice was based on a rigorous application of chemical principles. The gamma helix, therefore, functions as a crucial intellectual foil, its calculated flaws highlighting the calculated perfection of its sibling structure. Section 6 reinterpreting the physical evidence of alpha-keratin having derived their structures from first principles, Pauling and Corey turn to the available experimental data to validate their claims. This section focuses on the X-ray diffraction patterns of alpha-keratin, the protein found in hair and wool. The primary claim is that their proposed alpha helix model provides a complete and superior explanation for the key features of the keratin diffraction pattern, features that had remained enigmatic for years. A particularly vexing observation made by William S. Berry was a strong meridional reflection at a spacing of 5.1 angstroms. This was initially interpreted as the length of a single amino acid residue, which led to incorrect models. Pauling and Corey make the powerful claim that this 5.1 angstrom reflection does not represent a residue repeat but instead corresponds to the pitch of their proposed alpha helix, which they had calculated to be 5.4 angstroms, a value well within the experimental error of the low-resolution data. They further claim that a faint reflection observed at 1.5 angstroms corresponds to the unit rise per residue along the helix axis, another key parameter of their model. By reassigning the physical meaning of these reflections, they transformed confusing data into strong corroborating evidence. This section is a demonstration of the power of a good theory. It does not simply fit the data, it illuminates it, providing a new framework that resolves old paradoxes. The claim is that the alpha helix is the fundamental structural motif of the KMF group of fibrous proteins. Section 7 the systematic dismissal of other helical possibilities. In the final analytical portion of their paper, the authors perform a crucial act of intellectual housekeeping by systematically ruling out other seemingly plausible helical structures. The claim here is one of exclusion. They consider and reject helices with different hydrogen bonding schemes, such as those that would be formed by connecting residue N to residue N plus 2 or residue N plus 3. Their argument for dismissing these alternatives is based on steric hindrance. They assert through the use of physical models and geometric calculation that these more tightly wound helices would result in atoms overlapping, creating impossibly high-energy van der Waals repulsions. For example, a helix with 2 residues per turn, the p-helix, is rejected because the atoms of the backbone would clash. A helix with a hydrogen bond between residue N and residue N plus 3, which would later be described as the Frieton helix, is dismissed in their initial analysis on similar grounds of being too crowded, although this structure would later be found in short segments of proteins. The core claim is that their search space was comprehensive into the alpha helix and, to a lesser extent, the gamma helix, represent the only sterically and energetically feasible solutions within the constraints of a regular helical arrangement. This dismissal of alternatives serves to seal their argument, presenting the alpha helix as the result of an exhaustive and logical process of elimination, reinforcing its status as a unique and optimal structure. Conclusion: in evaluating the claims of Pauling and Corey's 1951 paper, one is struck by the sheer intellectual force of its deductive architecture. The work's profound and lasting impact derives from the rigor of its internal logic. The central claims planarity of the peptide bond, the geometric rules of hydrogen bonding, and the principle of residue equivalence in a helix form an axiomatic system from which the alpha helix emerges as an almost inescapable conclusion, the evaluation of their own proposed gamma helix, and the subsequent dismissal of other configurations showcases a self-critical and comprehensive methodology that lends immense weight to their primary proposal. The reinterpretation of the alpha-keratin X-ray data was a triumphant validation, demonstrating the theory's explanatory power, while later higher-resolution crystallography, most notably by Max Perutz and John Kendrew, would provide the definitive visual confirmation of the alpha helix. The 1951 paper stands as a monument to the power of theoretical chemistry to illuminate biological complexity. Its claims were not mere lucky guesses, they were the product of a deep understanding of chemical principles applied with extraordinary discipline and insight. The work's ultimate significance, celebrated by the Nobel Committee in 1954, lies in its successful argument that the intricate folds of life's essential molecules are not arbitrary or unknowable. Instead, they are governed by the precise and elegant laws of stereochemistry, a foundational principle that continues to drive the field of structural biology to this day.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.